I wanted to talk about what we talked about in detail last time, as we had started on a topic and then we moved on a little more. If you all remember, we started to briefly explain the topic of resolution and its impact on PET City. If you remember the PET City discussion, we mentioned that I am working on isotope, which has different characteristics compared to the technician. It relies on a completely different mechanism of conversion, where I have a material that contains an access number of protons. The proton converts to a neutron, producing a positron. This positron undergoes annihilation or interacts with the nearest electron, resulting in two gamma photons emitted at 180 degrees to each other. Happy Eid al-Adha. It is associated with an electron or binds with an electron, their masses according to Einstein's equation, which is energy to mass conversion, meaning their masses convert to energy. This energy is emitted in the form of gamma photons at 511 kilo electron volts for each photon present. So what I do is take a detector, place it on one side of the annihilation, and on the opposite side, I perform detection of these two gamma photons, which I call coincidence. This allows me to translate my image and localize the location of the annihilation. We talked last time about the different types of crystals, PGO and LSO, and discussed the parameters that determine the quality of the crystal and why a crystal should be good. For example, in spectroscopy, we use sodium iodide crystal. This sodium crystal has a stopping power and attenuation that cannot stop the 5111 kilo electron volts, but it can work on 140 kilo electron volts and can work on 364 kilo electron volts, which are the lower energy levels of gamma photons. So when I thought about it, for the 511 keV photon, I need a crystal with different properties to be able to stop the high energy gamma photon coming in at 511. So I started thinking about types of crystals like PGO or LSO, as we discussed last time. These are the different crystals available: PGO, GSO, and LSO. The most well-known types are PGO and LSO, which is Lysol. PGO can be found in companies like GE, while LSO is available in Philips and Siemens. We also talked about the dynasty of the second one. And we talked about the different types of crystals, and I mentioned that the choice of crystal type depends on several factors. First, when a photon enters the crystal, it interacts with an electron, causing that electron to move to what is called the conduction band. After that, it drops back down to the valence band. This downward process is what I call the decay time. I refer to it as the rapid decay time. This rapid descent helps facilitate a new interaction to occur. Just a moment, please, if you don't mind. Rashida, danger and deception. So we said that I have this electron that is descending, and its descent speed and decay time affect what? For example, in PGO, it takes 300 nNs, while in LSO, it takes 40 nNs. The shorter this time is, the faster the descent becomes, which increases the efficiency of the crystal in receiving new gamma photons. The light photons that come out as a result of scintillation or from this electron descending yield light photons, which I call the light photon yield, and the ratio of light photons differs between PGO, which gives you more light photons or has a higher ratio. This means you don't need a high dose for the patient to inject in order to give you a good signal or provide you with good image quality. PGO stops 511 gamma photons with a value of 0.95. LSO is lower at 0.83. Choose LSO for resolution, PGO for sensitivity. For example, you will find that PGO provides higher sensitivity while LSO offers better resolution. So if you want resolution, go for LSO. If you want sensitivity, go for PGO. In GE, for instance, you will always find that GE has slightly higher sensitivity, but LSO gives you more resolution in the image due to its shorter decay time. Now, we talked about crystals and the photon or radioactive material. In the patient, interactions occur, and not all photons go through annihilation, resulting in 2 gamma photons. We mentioned that Compton scattering can happen, and the detector may not detect both gamma photons from the same location. As we discussed earlier about true events, scatter coincidence, and random coincidence, if you have a true event, then annihilation has occurred with one photon going here and another going in the opposite direction, and both being detected is a true event for me. Now, when the photon exits, it undergoes Compton scattering at a certain angle, and the machine itself may not understand that it received a photon at one crystal and another photon at a second crystal, so it starts calculating the line of response. What happened in the place is that it tells you, yes, this is the place where a gamma photon was detected in this crystal. The second gamma photon did not get detected. It crossed from the opposite crystal for some reason. In the opposite direction of this crystal, there is another crystal, or another point, or another radioactive material located on the different side of the partition, which will also emit a gamma photon. So these 2 opposite detectors detected them at the same time. What will happen to the 2 gamma photons? This is called random coincidence. This always increases, or the rate of random coincidence increases with more activity when there is a high dose for the patient. Therefore, it is not advisable to use high doses at home because you will increase the scatter rate and increase the random rate. We have discussed this. Last time I talked about how to overcome random coincidences and scatter coincidences. There used to be something called 2D mode and something called 3D mode. What does this mean? I have the ring, as you can see, and we agreed that if you remember, here is the city and here is the bit. This is the city, because I will still talk about the benefit of the city and why I use it. So here is the bit, and inside it, there is a ring. There are rings present inside the bit itself, which are the circles we were talking about. Here is ring 1, 2, 3, or branches depending on the machine you are using. Okay? So if you use the space between these rings and take a cross section, you get a section inside this ring that looks like this. What do we take exactly from this? It's like taking a cross section within the range high. This means that this set of ranges has taken a section, and it will appear to you like this. This is a range, this is a range, this is a range. Each square here represents a range. Now there is something called 2D mode and something called 3D mode. So what is 2D mode? Remember the collimator? The collimator was used with something called a septum, which prevented the scattered photon coming from any angle. Any photon coming perpendicular to the collimator's hole was received, but those coming at an angle were not received. The same idea is applied to these ranges to increase the resolution and eliminate the scattered photons. You are only ensuring that the photons coming at 180 degrees are the only ones I will receive. As for those coming at an angle, they will be blocked unless your angle is weak, and then it will receive them. But what will this do? It will increase the resolution of the image, but at the expense of sensitivity. What is sensitivity? It is the number of collected or detected photons per time per administrative activity. For example, if I have 1 millicurie, will that 1 millicurie allow any of the doctors to enter? How many counts will I get from 1 millicurie in terms of detection in 1 minute? In 2D mode, the presence of the septum reduces the idea of scattered photons that will be detected, which decreases the number of photons that will be detected, thus reducing sensitivity. But if you remove the existing septum, I entered the 3D mode, which is the standard today. All devices are now in 3D mode. Therefore, the gamma photon coming from this angle, or that angle, or this angle, or that angle, can be received by different beams. Of course, one of the issues, as we mentioned, is that it provides a larger area for detection. If the gamma photon comes at 180 degrees in this direction, it will be received. 180 degrees in that direction will also be received from any direction. However, it increases the chance of detecting scattered photons, which is a drawback of the 3D mode. That's why we talked last time about the concept of energy resolution and timing resolution. The energy resolution concept through the pulse height analyzer tells you that the scattered photon coming to me, which underwent Compton scattering, is not coming to you with 511 keV. Instead, it comes with a lower energy. Therefore, you can adjust your window so that anything coming with low energy will be rejected. This way, you achieve energy resolution. As for timing resolution, it allows the two detectors, which are aligned with each other, to receive two gamma photons arriving in a very short time, like 9 nanoseconds. Picosecond is now referred to as timing resolution, which means that if you receive something in this window at this time, it's accepted. But if it comes outside of this time or after, it won't be accepted. This improves detection efficiency and enhances the resolution of your machine. This is what we talked about last time, energy resolution and timing resolution. Now the timing window, as it helps with random. Random is at 511 kV, but this is specifically for you to use to remove and it also helps you with the random, which is coming in kilo electrons, but coming at a different time means that the scattered photon arrives with different energy. So the energy resolution can filter it out. However, the random photon comes from another location. For example, it also arrives at 5111, but comes from a different crystal or detector that received it from another place. How do we differentiate between them? The one that comes from a different location arrives at a different time. Of course, if it happens to arrive at the same time, then it creates its line of response, which leads to misregistration or mislocalization. Therefore, it is always advised to use lower activity in PET-CT. Do not use high activity. In our current FDG cases, we can reach very low activities like 3 milli or 4 millicurie to reduce the probability of scatter and the probability of random events. This decreases the count rate detected, reducing the chances of scatter or random events, leaving only the true counts, which are the dominant ones and the ones you will rely on for localization. There are some other considerations. Also, when we talk about the subject, for example, I use something like fluorine. The positron that comes from fluorine will travel a greater distance than the positron that comes from other radionuclides when it collides with an electron. What does this do? It reduces your resolution. Why? Because when you localize the position of the annihilation, the closer the annihilation point is, the better. Look here. This is the positron. I'm sorry. This is the radionuclide that emits the positron. See this ring. This distance is the positron range. The closer the annihilation is here, not here. This radioactive material is here inside the argon. This distance is a small millimeter. But it can be larger if you use a radionuclide that emits a positron with high energy that can travel a long distance. So the annihilation point could be, for example, here. So when you see an FDG image and a gallium image, you will find that the localization and resolution are higher in the FDG image than in the gallium image. Why? Because of the positron range, as we mentioned last time. Another factor affected by non-collinearity is the two gamma photons that are emitted. They do not essentially exit at 180 degrees. The result is that the electron and the positron have momentum. They have angular momentum. Essentially, you are not capturing two stationary bodies. These are two moving bodies. As they move, collisions begin to occur, so the two gamma photons do not exit at exactly 180 degrees, but rather plus or minus 0.25 degrees. This part creates non-collinearity. If I have a detector here, then this angle, or the angle that the gamma photons have created resistance, created a difference, created resistance between the actual annihilation location and the location that will be designed by the devices. The calculated location of the radioactive source is different from the actual location. because the machine does not account for these angles. It assumes a 180-degree angle and draws a line, indicating where the event occurred. This reduces your resolution, meaning it increases the full width at half maximum, FWHM. The larger the FWHM value, the lower your resolution. For example, I told you that fluorine is a point source. I took a point, got a syringe, filled it with a radioactive material, and placed it under the crystal for scintillation. See this curve? It represents the full width at half maximum. Look here, it's about 1 millimeter. The fluorine has an energy of about 1 millimeter, and this is because you are using fluorine. The story begins with a quick brown fox that energetically jumps over a lazy dog lying comfortably near the riverbank. The scene is set on a beautiful sunny afternoon, where the fox, full of life and curiosity, explores the vibrant surroundings, taking in the warmth of the sun and the gentle rustling of the leaves. Almost, and its value does not decrease. It increases just like that? Exactly. So if its carbon is higher, that's why the image here is clear. You find in ammonia 1193 kiloliters of volts, and you can see the weights from the spectrum magnified. Here, oxygen 15 is very influential in your imaging process. There is also another factor. It's very important. He told you that I have the range of the crystal here, or the range that contains your crystal. He said that in the center, the resolution is different from the resolution at the periphery, at the edges. Why? He said that in the center, when annihilation occurs, it reaches here on this detector, and it gets detected, and that's the end of the matter. He said that at the edges, gamma photons can cross from one crystal to another. For example, here is a gamma photon passing from this crystal and entering this crystal, and it gets absorbed in this crystal. They call it a crosstalk, like a parallax idea, where it moves from one detection point to another. So what does this do? Of course, the crystal doesn't understand. The crystal that received the gamma photon doesn't understand, even though the annihilation point is here and the gamma photon is originally coming from here. No, it says, I will rely on this dashed point. So this reduces the resolution, which they call in the radial position or in the radial direction. That's why they tell you about your edges. The edges of the crystal or the edges of your field of view have reduced sensitivity and also reduced resolution and clarity. This is at the level of what is known and referred to as the field of view, specifically at the level of the ring. So in this view, if we remember, if there is a point source in half of the patient, it will have a greater chance of being detected. So its effect will be higher in the patient's half. If it is at the edge, the effect on the patient is lower, but in the patient's field, it is at the level of the transfer cell or at the level of your patient field in the Z direction, relative to you in center A, but with lower sensitivity. Briefly, at the edges, the resolution decreases. Why does the resolution decrease? Because of the crosstalk issue I was talking about earlier. These are the parameters that affect the topic. We will talk about them again because I am not discussing sensitivity and regeneration. The sensitivity in 2D mode in the collimator or SPECT, for me, is 0.5%, like in the other modes. The scatter fraction was 12%, which is good, but the scatter fraction was low, resulting in a decrease in detection. However, the sensitivity decreased due to the presence of the collimator in 3D mode. In this mode, sensitivity started to receive from more than one angle without any issues because there is no collimator, but it increased the scatter fraction to 40%. Okay, so guys, why is the adjustment process, including resolution and sensitivity, so important for our understanding and decision making? One of the factors that affects image quality is the point of attenuation correction, or why I use two methods. The gamma photon is emitted, and in order to receive it on my crystal, there are internal organs present, such as the liver and bone. What do these things do? They can cause attenuation and interact with the gamma photon. So, for me, the counts, which are the average of the gamma photons that reach the crystal, will decrease. Look here at the difference between these two images. This is a PET image, and this is a PET image, but this one is a gamma photon image after applying attenuation correction. What does attenuation correction mean? It means that you calculate the ability of each organ in the patient's body to absorb gamma photons and then compensate for the value that the organ absorbed by adding it to the counts you detected. For example, the heart or the liver. The liver caused attenuation, so it removed 1,000 counts from your image. When I know the amount of attenuation for the liver, I will reference the count. For example, in this image, the liver has low activity or is not illuminated. This image is inverted. The darker it is, the higher the activity. This is similar for the heart and the bladder. Now let's look at the other organs present. This is the liver I worked on. This liver here has low activity. Why? Essentially, the substance that goes to a large part of it goes to the liver and the heart, because anything that needs glucose and metabolism receives FDG. The bladder, of course, lights up, and the brain does too because it has high glucose uptake. So the liver here is hypoactive, and here it is illuminated with me. Why? What happened? I am taking a low-density whole-body CT scan, low dose. I don't need a diagnostic image. I just need an image that tells me how much attenuation each pixel in your image has and how many gamma photons it received. Then you perform the correction. If this pixel received few photons, it means there is attenuation. The amount of attenuation can create resistance, adding to the count in the image of the liver, making the liver image appear slightly brighter. For example, in the case of the skin, it seems as if it has taken on some activity because the attenuation of the skin is very low, which has reached you. If you rely on the image that you received from the home image, you cannot depend on it because the biodistribution related to emotions will be completely different. The distribution of the different radioactive materials will vary because here it depends on the attenuation part of the image. The part that has attenuation will give you fewer counts, so the lower counts will become hypodense, and the area with no attenuation will appear bright. Now, when you recognize that the pixel corresponding to your area has very weak attenuation, it subtracts the counts taken from any value, so the image remains true to its reality in this way. The idea of attenuation correction is that you take a CT image, which is a very standard cross-sectional image of the whole body, and you see each pixel's level of high attenuation. You will add counts corresponding to the amount of attenuation. For those with low attenuation, you will subtract the count corresponding to the attenuation, thus returning the image to its true state in this way. Is that clear, doctors? All right. This is the advantage of attenuation correction, especially if, for example, a patient has a dental artifact like this. This is the image after attenuation correction, and this is the image without attenuation correction. That's why you will always find in the bit city that it tells you there is an attenuation correction image and a non-attenuation correction image. The same idea applies here. There is an artifact that appears in this way. This is the non-attenuated correction image, and this is the attenuation correction image. Also, the dye has an artifact that comes from it after the attenuation correction. This is the steel image, which was also used. If you have gastric contrast or something similar, the previous one you have is the same idea. This is the non-attenuated correction, and this is the attenuation correction that occurs. Therefore, CT is very, very, very important in the process of attenuation correction. This is the first function of CT. The second function is that if you look at your image, you see that you are not exactly pinpointing. You see radioactive material and some black and white areas. If you are, of course, experts in CT anatomy, it shows you where the radioactive material is located exactly in the liver or in any loop in the kidney. So, the gamma camera image tells you how the activity distribution is, but the localization is where it is. Where exactly in the anatomy? Where exactly in the liver? Where exactly in the kidney? In the cortex? In the medulla? Or where exactly in the pancreas? Anywhere. This is the function of the CT, to provide a fusion between the PET image and the CT image, utilizing the biodistribution of the activity in the radioactive material, while simultaneously benefiting from the CT image to precisely locate the radioactive material. Okay, it hits. It hits. This is the image. In the Arabian context, it resembles the activity that belongs to every attenuation correction. But then we see the object.